So good afternoon. Today is October 27th and you're here for Econ 249. You're looking at a couple of events on the screen. So tomorrow, October 28th, there are about 3 different events that you should be aware of. The first one is a Federal Reserve info session, and the second one is Amazon Transferable Skills Workshop. Both these events are offered through the Career Center. If you're interested, you should RSVP for these events through that Hire QC, and I'm going to mark it here. So through Hire QC, you can register and RSVP for the events, and they're quite interesting. Again, it's just a way to network and get to know what's out there in the industry. The third event is also tomorrow, October 28th. It was given by one of your classmates. Fazia, if you're here, you can tell us a little bit about it. Otherwise, I'm going to explain that it's during your free hour tomorrow from 12:15 to 1:30. There's a Zoom link. What you need to know is this meeting ID and passcode. Sure, Karina, please tell us about it.
Everyone, so this event is basically with a social media influencer, and she's just talking about how she started her career and how she keeps engagement on an online platform. She's also an entrepreneur, so she'll be answering a few questions to our group members. So if you guys are interested in just maybe starting an influencer career or just getting advice, I think it would be a really good event. And yeah, she has about like 800,000 followers on her platform. So if you're interested in that, I really recommend you to come.
Thank you. And there's another event that is on Friday, October 30th. I will be attending it. It's more of a webinar. I'm not a panelist. You don't have to come in for the entire time, but you can stop in, listen to something anytime between 9:50 a.m. to 3:30 p.m. The theme is Women Leading in the World of Business. Again, you need to RSVP by 6 p.m. on Thursday, October 29th. But that's the link, and if it's not very clear, you can email me and I will send you more information. It's open to entire CUNY. It's a women's leadership conference to all faculty, staff, and students. So something very interesting that's going on around. There's another date that you should mark in your calendar. I haven't put it up here, but it's next week, November 4th, which is next week, Wednesday, during free hour between 12:15 and 1:30. It's a major minor fair. So this is the first time they're having this online, and it's a virtual fair where different faculty will be representing different departments. So if you have not declared a major, but you want to learn more about the major, or if you want to add a major, change a major, add a minor, this is the time to find out more about it. You can stop into the different rooms. You'll be given a Zoom link to ask questions. So this is happening next week, Wednesday, November 4th. I will send you another email to remind you, but just be aware that this stuff is happening. Before we start class today, you all know your second exam is on Thursday, October 29th. I sent everyone an email with a reminder about the chapters that are on the test, how to study, and sometime tomorrow I will send you a Zoom link so that you can have your camera on. Again, I'll mention this at the end of class today, but it's open book. You can use Excel, your notes, PowerPoint slides, whatever you want. You will be busy. You have enough questions to complete. So you won't have time to search for the answer. You have to study for it, just like you were going to walk into the classroom and take the test. So again, I suggest you prepare for the test before the day of the exam. Don't try to find the answer. You won't have enough time to complete the questions if you do that. Okay, so today I'm going to cover a different chapter. Khalid, you have a question?
Yeah, regarding the exam, are there going to be questions where we have to transfer over to Excel, do some work over there like the last exam?
Yeah, you can use Excel if you want. Yep.
No, but
Does
is
that
there going to
answer
be
your
questions
question?
where we have to use Excel? Like,
So the questions are very
is there going
much
to be certain questions?
like your homework problems. So if you're following, let's say, chapter 7, homework number 7, and you know you would prefer to use Excel for the question, then you can. You don't have to, I don't think, but it's optional.
Okay, all right, sounds
Okay, so today we're going to do a different chapter. We're doing chapter 10 today. Now, let me fix this. So, although chapter 10 is not on your test on Thursday, it's not on your test on Thursday, there's a lot of material here that is very theoretical. And it's not really application based where we're doing a bunch of calculations. It's really for you to comprehend certain concepts. And it's important because it's really the introduction to the next chapter after the second exam, so after Thursday. And also, it's a basis for you if you plan to take Econ 382, which is econometrics. Okay, so econometrics is really based on these next few chapters. You'll get a refresher of these next few chapters. That's why I tell my students, if you have to take Econ 382, take it right after this when the material is still fresh in your mind. So chapter 10, which we're going to cover today, is about sampling distributions. Now, again, a reminder, when I talk about this, more about imagining things, visualizing certain things. We're not going to be doing a huge amount of calculations in this chapter. And it's only a small section of this chapter that I will focus on. Okay, so reading from the slide, when taking a sample to investigate a population mean or proportion, we must realize that our sample statistic is only one possible sample that we could have taken. To learn more about the variability of the sample statistic, we have to imagine how the sample statistic would vary across all possible samples. One way to do that is to simulate lots of samples of the same size using the same population mean or proportion. Okay, a lot going on in this slide. Let's start from the beginning. First thing is this term, sample statistic. Does anyone remember what this means? What's a statistic? What's a sample statistic? So we know the difference between sample and population, right? Population is everything under consideration. A sample is a portion of the population. Priscilla, you say it's data collected to be studied. So that would be a sample. So you just answered the question as to what is a sample. That's my data that I collect to study. Okay. The result that I get from my sample, so I use some statistical method and I come up with the result. That result is called sample statistic. The result that I get from my population is called parameter. Okay, so we have sample, we have population. We have sample statistic, which is the result from the sample, and we have population parameter, which is the result from the population. So basically, we use the sample to come up with our result, to come up with our sample statistic, in order to make a conclusion or an inference about population parameter. That method is called inferential statistics, using the sample result to make an inference about the population parameter. Okay, now reading that first sentence, it's really saying when you take a sample to investigate a population. And what is it you're investigating? Some kind of parameter. It could be either mean or proportion. So you're using the sample to investigate population mean or investigate the population proportion. We must realize that our sample result, our sample statistic, is only the result because of that particular sample. If I took a different sample, I'm going to come up with a different sample statistic, the different sample result. So every time I take a new sample, I have a new result. So that's understood. It's happening because we have different samples. So we're saying that the sample results or the sample statistics vary from each other. There is some variability. Now, to learn more about the variability, so we want to know how much variability. Do they vary a lot from each other? Do they vary a little from each other? So that means we need to take many samples and kind of measure the variability across all the samples. If we measure that, now we can come up with a number that tells us, well, it doesn't vary a lot, or it doesn't vary a little. So we know something about the results from our sample. But how do we practically do this? How can we keep going back to the population and redoing this? It's really not practical when you have to do it. So what we do is we simulate it. We ask a computer to take lots and lots of cells of the same size using the same population mean or proportion. So a computer program does that. It could be some statistical software program that does that. So the idea is, yes, I know every time I take a sample statistic will be different, which means now when I make my inference about the population mean, population proportion, it might be based on that sample. So it's better to take many, many samples and see how different they are from each other. So that's what simulation does. A simulation is when we use a computer to tend to draw random samples from some population of values over and over. So it helps us understand how sample means or proportion vary due to random sampling. Okay, so if you just joined us again, it's a very theoretical concept, but we're going to try to visually understand what this means. Now, I keep saying both, two kinds of parameters here, means or proportions. So in this chapter, it talks about both. I'm going to start explaining just by focusing on mean. I think it's an easier concept to understand when you're talking about an average. So I'm going to start with mean. Now, again, we need to understand that every time we take a sample, we're going to have some differences. If we measure that variability, then we're talking about sampling distribution, which I'm going to get into. So I'm going to start a blank whiteboard. It's easier for me to write on here. So let's say that I want to find out what the average height of Queens College students are. Okay, I want to know what the average height of all Queens College students is. So of course, Queens College students would be my population, and that would be quite a big population. It doesn't make sense for me to go to every single individual and collect and measure their height. Chris, you have a question?
Hello, Professor. When the computer does this sampling model, does it also follow kind of the sampling population parameters, like 10% of the overall population?
No, it doesn't. So that's a good question. I'm going to come back to that later. Those are, I'm using the word parameter again, but those are parameters we have to put in to the program before we run the simulation. So we have to specify how many people we want, how many items to include in that sample while the algorithm creates that simulation. that's a good question. I'm coming to it. So now this is our experiment, right? I want to know what the average height is for all Queens College students. So we know the population is too large. I randomly select a few students. So I take, let's say I take, how many students? Take 15 students. I randomly select 15 students in my sample. And I take the 15 students and I measure them. And I come up with my result. Now my result is my sample statistic, which is the sample mean. So I'm going to jot down now, let's erase this. This is going to be my sample. And okay, so first sample that I got, I'm going to call it sample number 1. My results are my sample mean. So I'm going to say the first sample, when I took, oh gosh, I don't know why that happened. There's no way for me to just erase that. Guess not. Okay. You know what? I have to do this over because I'm going to spend some time here. Sample mean. So we have the first sample, and I measured each student, and I came up with the average for the student. So that sample mean, X bar, for that first sample, and I'm making these values up, let's say it came out to be 5 feet 7 inches. Okay. And I those students back in the population. And then I randomly select another set of 5 students. I'm going to say that my N, my sample size here, is 15, right? 15 students. So my second sample, when I measured those students, sample mean was equal to 5 feet, let's make it up here, 3 inches. Okay. And then I did it again. I put them back into the population. I randomly listed another 15 students. And when I measured them and took the average of those students, I came up with 5 feet 5 inches. Okay. Let's say I did this many times. Let's stop at 10 just for the sake of this question. And at the 10th sample, the average was 5 feet 5 inches. Okay. So this here, what you're looking at is a sampling distribution of means. So this is what you're looking at. You're looking at a sampling distribution of means. So a sampling distribution of means is the distribution of the sample means, right? You can see here it's a distribution of the sample means. If you actually selected all possible samples from the population. So I stopped at 10, but if I could get the computer to simulate this, and I actually selected every possible sample from the population and listed it, and what I have is a sampling distribution of means. Now I said that this chapter is very visual. You kind of have to imagine. I'm not expecting you to do this. I'm not expecting you to do any calculations right now, but imagine if we were able to sample 15 students from the population many times and get the sample means or the sample statistic. And then what if I took the averages of all this? What if I took all these values and computed the average? That would be mu subscript x bar. Mu subscript x bar is actually true population mean. I'm going to type it down here as well. It's actually the mean of the sampling distribution, which is actually the true population mean. So if I was able to get a sample from the population and do it many times and then get the average of all those samples, I have actually got the true population mean, which is an unbiased sample mean. So mu x bar is actually equal to mu. It's the average of all the sample means. So this method that I'm doing and what I've posted up here is called sampling distribution of means. So now I have a question. Which would be more surprising? Having one person in a sample that is over 6 feet 9 inches tall, or having the mean of a sample to be over 6 feet 9 inches tall? So Christopher, you're saying the mean would be more surprising to be 6 feet 9 inches tall. Okay, agreed. So what I'm saying is it very surprising to have one particular individual in this sample that is 6 feet 9 inches tall, or let's say I had X, let's call it X8. The eighth sample is going to be 6 feet 9 inches tall. So that's what my question is asking. And you all said that this would be very surprising. It's really highly unlikely that I would get a mean of 6 feet 9 inches tall. But it's possible to have 6 feet 9 inches tall individual in that sample. Agreed. So because that person is in this sample, that's probably why the sample mean is higher in the first sample mean compared to all the other sample means. That could happen. So that's one thing that you noticed. Okay. However, once I average it all out and come to mu x bar, that effect is really reduced. So I have really reduced it even further by the time I average out all those sample means. And this is with having 15 students in each sample. What if I had 100 students in my sample? So now I have 100 students in sample 1. I have that one individual who's 6 feet 9 inches tall in sample 1, and I end up with x bar 1 as a sample mean that is much higher than the other sample means, but still, by the time I average it out and find the mean of the sampling distribution, that effect is reduced. Okay, so any questions before I move on to the next slide? Okay, so that brings us to the next slide, which is exactly the same question I asked. Which would be more surprising, having one person or the mean to be over 6 feet 9 inches tall? So means have smaller standard deviations than individuals. So the point in that was we understand that you could have an outlier, you could have extreme values, you could have something going on within your samples, but the means are not going to vary as much. They're going to be different, but they're not going to vary that significantly. So the standard deviation, so I'm bringing that word back here because variability, the differences, that's bringing us back to deviation. So the standard deviation between the sample means will be smaller than the standard deviations among the individuals within the sample. Okay, so we need to recognize that we need to measure those standard deviations between the means. We need to measure either you want to call it variability or the differences, but there is some difference that needs to be measured. So that brings us to this slide. The normal model for the sampling distribution of the mean has a standard error equal to this. So I'm going to write something that is a little easier to understand. Standard error of mean is equal to standard deviation of sampling distribution, which is also called sampling error. Okay. So all these three terms mean the same thing. Standard error of mean is the same thing as standard deviation of sampling distribution. Okay, let's fix that. Which is the same thing as sampling error. All this measures the differences from sample to sample, the result from the sample to sample. So we know that although the sample mean varies from sample to sample, we know that they are less variable than the individual values in the population, but we need to be able to measure it. You have a question, Christopher?
Is this like finding the mean at z-score value on a curve?
No.
Okay.
So the z-score is from the previous chapter. So put that aside for now. Now what I'm trying to explain is how can we get to the true population parameter that you're looking for. So there are certain conditions to get to that true estimate. It's actually the basis for our next chapter, which will make sense when we get to the next chapter, which has to do with confidence intervals. But this is just saying that how can your sample, because we need to understand that every time we take a sample, it's different. How can we say that the sample is giving us the result for us to make a conclusion about the population, the entire population? There must be something going on with the sample that works. So there are conditions that we'll talk about later. But for now, understand that if we measure the differences from sample to sample, and we can minimize those differences or minimize the standard deviation, then our conclusion is accurate. So again, it's very vague the way this chapter is taught. It's a bit vague when you're trying to comprehend. So there's not much application. So it's a bit tough, but bear with me here. I'll try to apply it in the next couple of slides. So we saw now when we talked about average height of students, when you increase n, we saw that the single extreme value has less effect. So I'm actually going to write that in here because that's important information. As n increases, a single extreme value has less effect. So we need to understand that. As you're increasing your sample size, it doesn't matter now if you have an extreme value. So that's important to know. And now when you want to measure the variation in the sample means, okay, so I'm going to write it here. This is when variation is measured. When variation is measured, that means you have measured standard error of the mean, or you've measured standard deviation of the sampling distribution, or you've measured sampling error. So how do you measure it? Well, this is the formula you're going to use. Sigma subscript x bar is equal to sigma over square root of n. So that's this formula that you see here. Sigma x bar is the standard error of the mean, or it's also called standard deviation of sampling distribution, or it's also called sampling error. So now you have actually measured the variation in the sample means. Now looking at this formula, if I increase n from 15 students to 100 students, what's happening to my standard error? When I increase n, so when you increase a number in the denominator, what happens to that value? Sigma x bar, standard error of mean. So I'm going to write it here. My question is, as n increases, as I increase my sample size, what's happening to the standard error of mean? Increases, yes. Yes, so you can see it in the formula as well. When you increase a number in the denominator, that sigma x bar value will decrease. So that's interesting to know. As you increase the number of items in your sample, now the difference or the variability from sample to sample decreases. So that's important information to know. So that brings us to the next slide. This slide is basically saying the same thing, so I'm going to skip this. It's a sampling distribution model for the mean with the formula. So now we know that we need to increase our sample size if we want to get to the true population mean without much variability every time we take a new sample. Okay, but there are some assumptions and conditions that go with that. So now let's see what the first assumption is. The first assumption is that independence. The sampled values must be independent of each other. Okay, so we're assuming in our example of Queens College students, one measurement is independent of the other measurement. One outcome does not influence the other outcome. So we satisfy this assumption. Second assumption is the sample size assumption. The sample size n must be large enough. Now I'm going to come back to this because this is a very, very important condition. This is actually the basis of this entire chapter. It's the beginning of the next chapter. It's something that you're going to refer to when you're doing econometrics, economics 382. So I'm going to come back to this second assumption. The third condition is the randomization condition. If your data comes from an experiment, then the subjects should have been randomly assigned to treatments. So in our scenario, let's say I randomly selected those 100 students, or I randomly selected the 15 students. So that way I can come up with an inference that is unbiased. The last assumption is a 10% condition. If sampling has not been made with replacement, then the sample size n must be no larger than 10% of the population. Usually this is always met. That's the whole reason why you're doing a sample, using a sample, because your population is so large, the number of Queens College students is so large, so my sample cannot be larger than 10% of that population. So of course, it's less than 10% of the population, so that condition is met. Okay, so I'm going to come back to this idea with the sample size assumption, the second one. But let's move on to this next. Actually, before I do that, let me share a blank screen so I can write on the whiteboard. Okay, now in our experiment, I said that I'm taking a sample of students based on a population of all Queens College students. So first of all, I need to figure out the population. So my population of Queens College students, if I'm interested in height, and if I can imagine the heights of all these students, I'm going to say that most students are very close to the average height. Very few students are extremely below or extremely above the average height. So if I had to draw a distribution of heights for Queens College students, I'm going to have a population that is normally distributed. It's going to be a bell-shaped curve. And I'm taking my sample from a population that is normally distributed. So that's the first thing I'm going to write here. Sampling from normally distributed populations. So when I sample from a normally distributed populations, I can say that then sampling distribution of mean is also normally distributed. So if I'm sampling from a population that is normally distributed, then my sampling distribution of mean is also normally distributed. Now, what is sampling distribution of mean? Remember, we had those two columns, X and X bar, or sample 1, 2, 3, 4, 5, all the way to 10, and then the sample mean for the first sample mean for the second sample, and so on. So that was my sampling distribution of mean. So I'm saying if I draw that sampling distribution of mean as a graph, those two columns, I would have this x-axis as the sample means, all the x bars. And if I took the average of all those sample means, that would have been my mu x bar, right? Which would be the true population mean. And if I initially had 15 students in my sample, I would get a graph that looks like this. That's my distribution of the sampling distribution of means. This is when n is equal to 15. Okay, and this is my center. So it's not perfect, but if you can imagine that this is a normal distribution. Then I said I'm going to increase n. So let's first make n something else. Let's say I make n equal to 25. Now when I increase n, my standard error is smaller, which means it's not as spread out. Variability is less, which means it's closer to the center. The values are not as far away from the center. That's because I increase n. What if I said that I am now taking 100 students in my sample? So now n is equal to 100. So you can see here that as n increases, the sampling distribution of mean becomes narrower and more bell-shaped, and the standard error is less, and the true population mean is closer to the individual values. Okay. Answering your question, Christopher, you said, does this follow the 68, 95, 99% rule? Yes, it does, but you're still imagining that x-axis as z when you're talking about the rule. Here, try to imagine it as the sample means. So I'm talking about x bar. Everything on the x-axis is a sample means. So now, this is when you're sampling from normally distributed populations. What happens when you sample from non-normal populations? So let's write that down. Sampling from non-normally distributed populations. Okay. It's we have to acknowledge this. Although I said that many populations are normally distributed, there are times and instances where you cannot assume that everything is normally distributed. So you might be dealing with a non-normal distribution. Maybe it's skewed, maybe it's not normal, maybe it's a binomial distribution. So there is a theorem in statistics that is called the central limit theorem, and it deals with this situation. So the central limit theorem states that as the sample size gets large enough, the sampling distribution of mean, so that's what you saw on the left side here, the sampling distribution of mean is approximately normally distributed regardless of the distribution of the individual values in the population. So I'm going to say it again. This is the central limit theorem, which is really the basis of this chapter and the next following chapters, and what you're going to refer to in econometrics if you take economics 382. So the central limit theorem states that as the sample size gets large enough, the sampling distribution of mean is approximately normally distributed regardless of the distribution of the individual values in the population. So if I draw this, I'm saying that you're dealing with a population that is not normally distributed. And then you're going to sample from that population that is maybe skewed. Perhaps it looks like this. And when you take your sample from that population, you're going to have a skewed distribution as well. So the center would be mu x bar, which is actually your true population mean. And this is your center. So let's make that the center. So the central limit theorem says, as you increase n, you're going to end up with a distribution that looks like this, that is normally distributed on one condition, as long as your n is large enough, your sample size is large enough. So the question is, how large should n be? N must be greater than 30. So mathematicians were able to prove this theorem, and they said that as long as n is greater than 30, then your sampling distribution is nearly normal. Then you can continue with normal distribution. And it's quite significant because this is saying across all distributions, it doesn't matter if you are dealing with a normal distribution or not a normal distribution, as long as your n is large enough. So this is where that second condition was with that slide. It said the sample size n must be large enough, so it must be greater than 30. And this is the central limit theorem. Okay, so this is bringing us to the right track in order to get to our population parameter. The whole goal is trying to estimate, make a prediction about the population. Okay, any questions before I go back to the slides and all this gets erased? No questions? Okay, so going back to our slides. So this is what I said, and this is the sample size assumption. So let's look at this. Simulating the sampling distribution of a mean. Let's say you have one die and you toss it 10,000 times. Of course, you cannot manually toss it. You get the computer to toss it, so it's a simulation. You have 6 different possible outcomes, and the y-axis says it's the number of tosses, so 10,000. If you draw your graph, you end up with something like this. This is not exactly a normal distribution. It's telling you that it's all about the same heights, these vertical bars. So it's more of a uniform distribution. Well, what if you now have 2 dice and you take the average of the 2 dice? If you take the average of the 2 dice and you toss it 10,000 times, and on the x-axis you have all the averages. Remember, we're talking about the means. So now if you talk about the averages, you get a shape that is more triangular. So it's a triangular distribution. What if you increase n to 5 dice? So this is saying that as the sample size gets larger, each sample average tends to become closer to the population mean. So the sample average, the differences get smaller and smaller, so the standard deviation gets smaller. So now you have more of a bell-shaped curve, and you're actually approaching the true population mean. So now you have a normal model. So the next slide really says everything you need to know about the central limit theorem. It is true regardless of the shape of the population distribution. Okay, so now what we're going to do is we're going to apply these concepts to our first word problem for this chapter. And again, the only reason I'm doing this exercise here is because you're going to need it for your homework for chapter 10. But now the homework is not due till after your exam, so you really don't have to start on this yet. I want you to focus on studying for the test on Thursday. So this is very typical of a question that you would see for chapter 10 homework. Okay, reading. According to recent studies, cholesterol levels in healthy US adults average about 215 milligrams per deciliter, with a standard deviation of about 30 milligrams per deciliter, and are roughly symmetric and unimodal. If the cholesterol levels of a random sample of 42 healthy US adults is taken, are conditions met to use the normal model? So to answer your question, Priscilla, this is not going to be part of the second test. Okay. So according to recent studies, cholesterol levels in healthy US adults, you're given the average. Okay, so that means mu is equal to 215. Okay, that's your average that's given with a standard deviation of 30. Okay, so you're given sigma, and sigma is 30. So 2 bits of information. Now, your population is all healthy US adults. Okay, we have to bear in mind that that's the population. How do we know this? Because how do we know the average and the standard deviation? Because they have looked at recent studies, and they already know that the average is this much. You're also told that it's roughly symmetric and unimodal. Okay, so you know that you're dealing with a normal distribution because you're told that it's symmetric and it's unimodal. Now you're told that if the cholesterol levels of a random sample of 42, so that means n is 42, that's your sample size, are conditions met to use the normal model. So let's start with the conditions met. Randomization. Do you think we met this condition? How do you know? Exactly. It says here random sample, so subjects were randomly selected. It's not biased. So I can say check, we've done the randomization condition. 10% condition, well, if my population is all healthy US adults, that must be millions, healthy US adults in the US, millions, and I'm only taking 42 in my sample, and I have definitely met the 10% condition because I have under 10% of my population. So that's met. Large enough sample condition. Is that met? So have I met the large enough sample condition? Yes, because n is greater than 30. I agree. So with this condition, right now we're only focusing on means. I have not mentioned anything about proportion. So I'm going to mention it now so that you have it in your notes. You might need it when you're doing the homework. If you're dealing with proportion, instead of the large enough sample condition, you might have to check it this way. N times P must be greater than 10 and N times P 1 minus P must also be greater than 10. So if those two conditions are met, then you can continue. If they are not greater than 10, that means you need to increase your sample size to make that condition met. So that's also another way of checking the large enough sample condition when you're dealing with proportion. Okay, so when you're dealing with proportion here. Okay, moving on to the next slide. So the question says, what would the mean of the sampling distribution be? So the question is asking you, what would the mean of the sampling distribution, X bar? What would that be? Okay, so I'm going to put this as a poll and you're going to give me the answer. So your choices are 30 milligrams per deciliter, 215 milligrams, or cannot be determined. Okay. So make your decisions. Okay, 30 seconds. Okay, I'm going to stop the poll here. So most of you can see here that 215 is the correct answer. So mean of the sampling distribution mu x bar is equal to the true population mean mu, which is actually given in the question. So that's 215 milligrams per deciliter. Okay, the next question is saying, what would the standard deviation of the sampling distribution be? Okay, so the standard deviation of the sampling distribution is sigma x bar. And that formula I showed you is sigma over square root of n. So sigma over square root of n. I'm going to give you the poll again. And you can answer that. What would the standard deviation of the sampling distribution be? Okay, 30 seconds. Okay, I'm stopping the poll. So most of you got the answer right. The answer is 4.629. Okay, so this is the answer. You would take this 30 and divide it by the square root of 42 and get your answer. Any questions for me so far? So now you know the standard deviation and you know what the true mean would be. So now there's one more question. Since you know those two, what is the probability that the average cholesterol level will be greater than 220? So the question is asking you to find the probability. Now, before this chapter, you would have set it up like this, the probability that it's greater than 220. And what's that probability? So this is how you would have set it up in chapter 7, the previous chapter. But since this is asking for the average, it's asking for x bar. Probability that x bar is greater than 220, what's that probability? So now I'm going to open a blank whiteboard so that I can write. I have more room to write, and I'm going to answer this question. So here's the board, and you're asked to find the probability when the average cholesterol level. So be careful when you're doing your homework for chapter 10. It's not just finding the probability, but you're finding the average of x bar. And you're asked when it's greater than 220, what's that probability? Okay. The next step is very similar to how you're used to transforming x into z. So we would have done x minus mu over sigma to get our z. But the difference is here we have x bar, and it's not mu, but it's mu x bar, and it's not sigma, but it's sigma x bar. So that's just the slight difference. So now we have 220 minus mu x bar, we were told in the question, is 215. We found out what sigma x bar is. That was 4.629. and we have to find that probability in order to get our answer. So next step, now this becomes Z. So now, Christopher, you're right, because now we've transformed our values on the x-axis into z-scores. So now Z is greater than, what's this value? Can someone give us this answer? 220 minus 215 divided by 4.629. Elizabeth, you said 1.08. Thank you. 1.08. Okay, and the question is, what's that probability? Okay, so now I'm going to draw my graph. So even if you decide to use Excel or table, you still have to draw your graph. I'm going to mark my Z value of 1.08. And when I look up in the table for, oh wait, one more thing, greater than means I have to shade to the right here. So we're interested in that area. Okay, when I look up in the table, Z is 1.08. I find it from negative infinity, and that value is 0.8599. So you could have used the table or you could have used Excel, whatever you're comfortable with. And that's what I found. That area, the unshaded area from negative infinity up to that point is 1.08. So that's not the final answer because I'm interested in 1 minus 0.8599. Can someone give us that answer, please? Thank you, Dong Yan. So you're saying 14.01%. So 1 minus 0.8599 is 0.1401. So to answer the question, what is the probability that the average cholesterol level will be greater than 220? That probability is 14%. 14% probability that the average cholesterol will be greater than 220. So this entire example was using means. I'm going to do a quick example. We have about 10 minutes by illustrating how to use proportion. So you don't need to memorize anything. You don't need to follow the formula and all that. But let's just do a practical example ourselves. Okay, so I'm going to start with the question, a poll for this class. And I'm going to ask you, let me see. If you could vote in the 2020 election, who would you vote for? So this is a question I'm asking. If you could vote in the 2020 election, who would you vote for? Now, I understand that there are more than 2 candidates on the ballot. There's actually 4 candidates who have qualified to appear on enough state ballots to win a majority. We have Donald Trump representing the Republican Party. We have Joe Biden representing the Democratic Party. We have Howie Hawkins representing the Green Party, and Joe Jorgensen representing the Libertarian Party. For our purposes, I'm only going to put 2 candidates. And you don't have to influence anyone. Okay, so we're going to vote in our class today, and then I'll tell you the reason why. So when I see this, I don't know what your answer, who chose what. I just know that you participated. I don't know if you get something right or wrong, but I do know that you've participated. Okay, so I'll keep it open for another minute. And then I'll share the results with you, and then we'll try to predict something. So the question is, if you could vote in this 2020 election, who would you vote for? Okay, I have 22 students who have not voted. Okay, I'm going to close the poll in a little while. Okay, stopping the poll here. Okay, so you can see here that we had 48 who chose Biden. We had 11, and we have 59 students who voted. Okay, so now I'm going to take this information and go to Excel. So I have to share my screen with you. Okay, so here we are. In this class of 59 votes, we have 48 for Biden and we have 11 for Trump. Now, according to 538.com, so you can do your research and figure out what that site says, they do pretty conservative predictions. It states that Biden is favored to win the presidential election by 52%. Okay, not that he's going to win, but he's favored to win the presidential election by 52%. So I'm going to go with that number. Okay, now, so I'm saying that the true population proportion is 52%. That's because, and I'm getting it from them, the conservative prediction. True population proportion is 0.52. So my question to you is, what is the probability that more than, I'm just going to say 60%, what is the probability that more than 60% of my students in class today will choose Biden? That's my goal. What's the probability that more than 60% of students will choose Biden? So you're the sample. I took you as the sample. So let's first figure out the assumptions. Did we cover the independence assumption? So I'm going to say yes, your votes were independent of each other. You didn't discuss it with each other. You didn't influence each other, so they're independent. Second thing is random. Well, I'm going to say yes, it's kind of a random selection. Uh, you could argue that it was biased. I purposely took students who are more analytically oriented because they're in a statistics course, maybe not so random. What about the 10% condition? So yes, I think I've met the 10% condition because if my population includes all Queens College students, all university students, all New York City folk, all people in Queens, then I'm definitely under 10% of my population. So I'm fine with that. What about the large enough sample size? So you can see here that n is 59. It's greater than 30, so I'm good. But I can double check with my, since I'm dealing with proportion, is n times p greater than 10? So n is 59 times 0.52. It is actually 30. So that's greater than 10. Also, is n times p 1 minus p? Is that greater than 10? If you want to check, that's also greater than 10. So I'm okay with my assumptions and my conditions. So now I'm going to answer this question. What is the probability that more than 60% of students today will choose Biden? So I'm asked to find the probability, and this is proportion, the true proportion, P. What's the, sorry, not the true proportion, the sample proportion. Let's call that the sample proportion. what's the probability that the sample proportion will be greater than 60%, right? That's what we have to find. So that's what I need to find. What's the probability that the sample proportion will be greater than 60%? Now I'm going to bring this back into the whiteboard and solve for it there. Okay, so I'm going to stop sharing here, coming back here. Let's write this out. So I have to find the probability that my sample proportion PS is greater than 60%. So I showed you the first example using means. Now I'm going to show you how to do it with proportion. So in the same way, we need to transform this PS into Z. So the formula is PS minus that true proportion, P, divided by P times 1 minus P, this denominator divided by N, and the whole denominator square root, greater than. So now I'm going to do the same thing on this side of the sign. We take 0.60, which is the sample proportion, minus true proportion. So as a reminder, I'm going to put this here. I said the true proportion is 0.52, and I got that because of that conservative prediction. So this is 0.52 divided by 0.52, 1 minus 0.52 divided by, in our example, N was equal to 59. Okay, so I'm going to put 59 here. And someone come up with the answer for us, please. The denominator is a square root here. So can someone do 0.60 minus 0.52 divided by this entire thing square root? 0.52 times 1 minus 0.52 divided by 59. Okay, Rad, you said 0.00423. Okay, anyone else wants to double check? That's the same answer you get. 0.00423. Anyone else wants to check that? So I'm going to draw my graph. Okay, so that's not right, Brad. We're going to go with the other value that everyone else says. Okay, so cross this off. Let's go with 1.23. Okay, yep, that's the denominator. Okay, so this is 1.23. Okay, so I draw my normal distribution. That's not great, but we can make that, fix that. Okay, let's say this is 1.23. And since we said greater than, I have to shade to the right. Okay, so that's the area, the probability that I need, this orange area. So I'm going to look up in my tables for 1.23. And when I look up in my table at 1.23, I get 0.8907. Okay, just double checking that. Yep. So that means what's the area from 1 minus 0.8907. Does anyone have that answer for us? Okay, thank you. We're saying 10.93%. So seems like that's the answer. 10.93%. Okay. So if I ask the question, what is the probability that more than 60% of students in class will vote for Biden? More than 60%. The probability is 10.93%. Not a huge probability. The probability that more than 60% will vote for Biden is only 10.93%. So now you see how you can apply all these different concepts. You know, don't just go with the polls. It could be a very slight margin, so make sure you go out and vote. It could be nothing like what we just did in class today. Okay, so I'm going to stop here. You can email me with any questions. I'm stopping the